First of all, I'm extremely happy to be here. My plane was cancelled and so on, and I took a night train, but I got here and I think it's worthwhile. The robotics, how robotics is organized in Europe is a little bit complex. So we have the association on the top. That is the outcome of joining forces of the academic robotics network, EURON, and the industry-led sister organization Europe. In 2009 or so, we decided to join forces, and 2 years ago we made a legal association. And the trigger to make a legal association, which is EURobotics, was to be able to engage in a contractual public-private partnership with the European Commission, and that's what is SPARC. So, roughly speaking, EURobotics is like NASA, that's the organization that does a lot of things, and SPARC is the biggest project like Apollo was for NASA. That's a little bit the context. The most visible activity of the association within that public-private partnership is this multi-annual roadmap. So that's the thing we have to do in the contract with the European Commission, to provide the community input to the Commission so that the Commission can draft the calls for project proposals. That's how the whole structure works. So the association is basically forever. SPARC has the lifetime of Horizon 2020, and then the roadmap is to be updated yearly. From this community, there is a very active group on Cognition. So Cognition is one of the 10 or so abilities, that's here cognitive ability, one of the 10 or so abilities that we consider to be important for a robot research and also industry to be focused on in the coming years. So the abilities are really in the middle of application domain requirements. So what do markets want? Where is the money to be gained? And on the other hand, the technology push from research. And so the abilities are always multimodal integration of different technologies, taking into account multiple application domain requirements. So that's the architecture of the whole thing. Today I will be speaking both as a researcher and as a representative of the PPP towards this community, the cognitive systems. Roughly speaking, one-line summary, the future of robotics is going to be cognitive robots. I'm not saying that because I'm here for you. I think that's going to be essential. And I'm going to try to explain what I mean with that and how we could go to that direction and where the industrial exploitation of that cognition can be or should be. That's the summary of the presentation, because the emphasis or the reason of Europe, but also your national countries, to put money in research is not because they like you to do research and go to conferences, but eventually it is to turn public money into knowledge and knowledge into money again. And you should not forget. What I often say to the robotics community is the PPP will be the last opportunity for the robotics community, academic and industrial, to prove that we are worth of public money. If we do not really realize a big revolution in robotics, I don't think the European Commission is going to fund more robotics research as a very visible research area. And I would even advise them not to do so. So the expectations are high. There are opportunities to realize them, but the important thing in the association, and especially in SPARC, is how do we make eventually money out of that research? That may be something that you think you're far away from, but you shouldn't. So, these are the 4 objectives. The first 3 I already explained a little bit. The fourth one, I'm still interested in getting to know how you feel towards that aim. To what extent is your community, the community present here, how much are you motivated to turn your research eventually into money? You don't have to do it yourself, but are you ready to cooperate with people and organizations and industries that do? That's a very important thing you should reflect about for yourself, and you should also try to communicate that to me. What I've learned the last 25 years is that the most interesting research questions are always in the applications. We are solving the easy things for years already. I've been in 75 PhD committees, and as the chairman of the EURobotics PhD Award, I've seen in detail hundreds more. 99% of those are solving academic problems. 99%. That's not too bad in itself. The problem is that most of these people even don't know what real problems are. And that's really a gap. What are real problems out there? And every time I meet a new company and talk about their robotics requirements, there are always fundamental questions arising. And the number one question, but I can't formulate it like this: how do we introduce cognition into our systems? But no one uses the word cognition, but that's the number one need. It is formulated like user-friendly interfaces. The machines have to diagnose themselves. They have to explain to the operator how well they're doing. That's the kind of requirements. It all boils down to progress in cognition. Today I'm going to try to give a road towards that, which is, I think, feasible within a couple of years, and to which I hope you all can see your role in realizing this. Cognition is I don't know whether you have a perfect definition of that, I don't, but this is how cognition is defined for the time being in the multi-annual roadmap. So a lot of abilities to interpret and to reason and so on. I have a somewhat more pragmatic definition of cognition. I would be happy if within 3 or 4 years the robots that are out there in industry or in homes or in care organizations are able to explain to humans and in human understandable terms what they are doing. What the robot is doing currently. Not saying I'm running program XYZ. No, no, that's what I'm doing. Why the robot is doing something? Because very few actions are just standalone. More and more robot tasks become very complex. You have a lot of subtasks that have to be done. But why is the robot doing what it's doing now? To a large extent, it is because something else will follow later. Current robot systems can't do that. How well is it doing it? That's something that I see no research addressing that. What are quality of service measures of what the robot is doing? What it most likely will do next? Also very important, especially in the context of human-robot interaction. If the robot is doing something and the human in the neighborhood or as a user of the system has no idea what the robot is going to do, that's a very dangerous robot. Or it's a very ineffective robot, because you will have this mode confusion between expectations of the human and activities of the robot. Another important thing, most of our robot systems are underused. Mobile manipulators or mobile platforms with 1 or 2 arms, a sensor head, a lot of other things, those systems are becoming available, also commercially. But most of these systems are always doing one single stupid thing, and 80–90% of its capabilities are not being used. So robots could do a lot more. Now robots are still moving like a robot. I'm going to take the bottle there, I turn, I drive, I haven't used my hands, I'm going to scan. That's how robot systems are being programmed now. That's not the way it should be done. Robots can do a lot more. Robots should also be able to explain what they are taking into account in this action. When the robot is doing that, to what extent is the robot aware that there is something here? To what extent is that important for the execution of the task? To what extent is the robot controller taking that influence into account? It's all things that are not yet there. We have a lot of demos that suggest that robots can do these things, but I don't know of any system that is really able to explain that to you. The last one, what is the role of the robot in a system? Because single robot applications, that's an exception. The future is all about systems of systems. And it will not be heterogeneous sets of robots. It will be humans, different kinds of robots. So what is the role of one particular robot in the whole system? For me, that is the definition of a cognitive robot. In the question session or afterwards, if you do not agree with these things or you have other suggestions, please talk to me, because I'm looking for a definition that industry people can also understand. And fundamental researchers in cognitive systems are willing to discuss about. So I hope to find a pragmatic discussion that can make bridges between communities instead of putting walls behind them, between them. I also introduced the concept of a skill. So for me, a skill is the way that a robot is programmed. So it's computer representation, it's a program that can connect symbolic descriptions of the activities with the real execution of these things. So that means you have a description of the task of a robot in natural language, for example. The skill is the kind of software we have to develop that can take that as an input, turn that into actions of the robot, and the other way around. Can interpret the motion of the robot, the actions of the robot, and explain it in the same symbolic level. That's what I call a skill. It turned out that this word skill is also extremely useful in the political debate. So maybe many of you have noticed that in several countries all over Europe, the politicians have started to form an opinion about the connection between funding robotics and creation or loss of jobs. In some countries there have been very heated debates, like in the Netherlands last couple of weeks. And I think the discussion should not be about robots taking jobs, but about robot skills replacing job skills. That's a lot more continuous space of discussion. It's also something that is a lot easier to go and discuss with people that are involved, because some or a lot of the low-wage workers would definitely be interested in having robotics technology that can take over some of the dull skills or the annoying skills or the dangerous skills without replacing them completely. So the discussion of skills, I think, is a lot better than robot systems or robots as a whole. Okay, so that's all one of these things I tried to bring in to form a terminology that is useful for discussing research, for discussing with industry, but also the socio-economic context, politicians, other stakeholders, labor unions, things like that. Okay, that's the hypothesis I just introduced here. It is a hypothesis. So if you, again, if you do not agree with this, please let me know. I'm always interested in being refuted with respect to my hypothesis or to express them more clearly. There are a couple more hypotheses during the slides, so I'm not going to repeat this invitation every time. Please do so later on. I'm going to first show a couple of demos. These are skills, but they fake cognition. So I'm not going to show a lot, but just to give you an example of the kind of research that our group is working on. Okay, here you see some examples where the robots are doing complex things. So none of these motions is completely pre-programmed. So we start with a symbolic description, very engineering-like, not natural language-like. And the whole motion, the sensory motor control, is decided online. So all of these things, this not pre-programmed, no planning there except planning at the declarative task level. We can explain everything the robot does, and when it does something well or not well, we as developers can explain it. The systems themselves have no clue. They're just running code. So that's the step change I'm talking about. We need systems that explain what they are doing to the operators. And that kind of robot controllers, that's going to be the next market in robotics. Okay, how do we approach this? Another hypothesis or our research approach is we have to bring in cognition, and the first necessary step is the representation, the formal representation of the knowledge. The knowledge that's now in the head of the people that develop the systems, we have to represent that formally. That's not full cognition, but I think it's the first step, and especially in a close to market context, that's the first step. There are these 5 types of knowledge: tasks, platform capabilities, environments, object affordances, and common knowledge. With 2 M's is already enough instead of 3. The hypothesis here is those 5 row domains, row categories, are enough to start the next generation of commercial robot controllers. I'll give some more explanation about that later. So it brings a little bit of structure, but on the other hand, not so much. There is also a hierarchy in the complexity of knowledge representation. I'll say a little bit more about this. So the hypothesis there is this is the right set of concepts to develop the next generation of cognitive industrial robot systems. The skill there is the skill, the human skill, the programming skill to integrate all these things together. So this community is probably aware of the concept of affordances. I think affordances are not a property of the objects, but are a property of the whole integration. In psychology, the concept of affordances was created and attached to objects because it was in the context of humans working with objects. And there, all the rest, the platform capabilities, the tasks and so on, you can assume that all the humans have a very similar set of knowledge about that set of sensory motor capabilities. In robotics, the affordances are not part of the objects. They are part of the whole system. So they are part of the skill. But that's a terminology discussion that we could also have later if you're interested in that. I make a link with one of the presentations of this morning. So the multimodality of these representations, it's what I interpret, or how I interpret that is, if you program a robot, you have to connect all these different things together. It's the whole thing, the whole sensory motor control system together. And not just part of it is the whole thing together. The second part of our research approach is that every task, so one of these 5 things, what the robot should be doing, every task is a constraint optimization problem. I'll give a little bit more information about that in a later slide. And where does the knowledge come in? The knowledge comes in the first phase, in configuring this constraint optimization problem. Again, the example of going to this bottle, when I'm doing it, I'm optimizing things like energy efficiency, time, position accuracy. And for example, here, it's not so important how exactly I move my hand. It's only towards the end of that subtask that position accuracy becomes important. And if you do that yourself, you feel that your sensory motor control system is configured differently here than here. There's no robot system that does that adaptation already. So most of the robots, especially industrial robots, they're spending a lot of energy moving from A to B, while the accuracy there doesn't matter at all. Most of the robot systems are actively wasting a lot of energy standing still. Right? So that's the kind of configuration or reconfiguration of the sensory motor control that should come from the knowledge context. Okay? So knowing in which context a certain task is being executed should define how the sensory motor control is configured. It's not going to realize the sensory motor control, it's going to configure it. These are all things that are very close to industrial practice. It's just a matter of making this step change and redesigning the control approaches. Again, these are research hypotheses, but we've been working along these lines for a couple of years, and I have no reason to change this hypothesis for the time being. Closer to market, it's most, I think, the low-hanging fruit, the economic value, is going to be in having this knowledge available. Learning, adaptation, and so on, that's a next step. That's not so close to market. That's where a lot of research is still to be done. But the knowledge representation part of cognition, that's definitely very close to market. Here, I'm going to spend one slide on looking at task as constraint optimization for, problems. This is formalization. The important thing are the last two, the tolerances and the solver. So we look at the research of constraint optimization. It's basically focusing at solving the problem. Very few of these R&D results allow you to configure the tolerance. When is the problem solved good enough? That's surprisingly one of the things that's very much not there in the research on this. The last thing, the solver, that's about a specific algorithm to solve the problem. And there is a lot of knowledge about the algorithm that is also not exploited. And so the algorithms you're using are part of the resources of the robot platform. And the robot should also have knowledge about its own algorithms and about its computational infrastructure and so on. But I'm not going to go into too much detail there. Then what does a skill do? So the skill adds things to this task. And the 5 things I've put there are basically all equally important. When you make a certain skill, you want to solve a certain task with a certain robot in a certain environment with certain objects. So one of the very important things that the skill has to do is to make that context explicit. What are really the boundaries, what is the closed world in which the robot system is able to solve that problem? What is the closed world in which the robot is able to explain what it is doing, how well it is doing, what it's going to do next? And the human has to know about that context. One of the biggest problems between humans and complex systems is that humans have no idea what is the closed world in which that engineering system has been developed. So that's a very important part of the skill. I don't know of any research that tackles that explicitly. What it then does in that context, that's what I said before, it fills in a lot of these parameters of this constraint optimization problem, control gains, accuracies, and things like that. It also has a finite state machine, between quotation marks. It has something to let the system change its behavior. Change its behavior in these engineering terms means switching to another constraint optimization problem with other objective functions, other tolerances, other constraints. The human also has to be aware of that, which behaviors the system can have and how is it going to change and when it has changed. So that's a very important part of bringing cognitive systems closer to economic reality. The whole skill with this explicit context, that is implicitly also useful to think about prediction and expectation, because we have explicitly programmed in behavioral changes. We have explicitly programmed in which parameters, objective functions, constraints are monitored and which ones will trigger change of behavior. But these objective functions or this problem can also be solved in simulation. With the current state of the robot, what would the robot do if the world would evolve like it is now? So it's also very important for prediction. So also there are some links with presentations of this morning. Cognition means being able to make predictions, to have an idea what is going to happen in the future and how you're going to react now to what you expect that is going to happen in the future. Last but not least, every skill comes with one particular implementation to solve the constraint optimization problem. And something I've learned the hard way is there's such a large variety in solvers, even if the problem looks quite similar, you have to know about the properties, the behavior of the numerical algorithm. For example, simplest one is it a stop anytime algorithm? Is it something that can be distributed and things like that? Intermezzo, this would be a symbolic constraint optimization problem. I spent 2 hours with students in my robotics class to really find out how much knowledge and constraint optimization assumptions or models are behind this single figure. So putting a piece of furniture together, we understand that there's a whole body of knowledge behind that single figure. This is a constraint optimization problem, not represented in an engineering form, but in a more natural form. Nevertheless, that's not so far away from reality. Good. When you have this constraint optimization problem, it almost immediately gives an answer to the questions I was putting there, which is also not a coincidence because I knew that this was going to come. But constraint optimization problem, if you go to the effort to make that explicit, it also gives the robot all the structure, all the formalizations, everything it needs to start doing the explanation. Yeah. What it can do even more. One of the other advantages of constraint optimization, and I think that's also a model that is used to explain how humans move, constraint optimization problems are composable. That means I can reach to the bottle as I did before and at the same time speak in the microphone and at the same time look at you. These are just 3 tasks. I can compose them together. The system itself solves it, taking into account its own structural mechanical constraints. It is bidirectional. I was very happy to hear that in the speech this morning. Every system interacts bidirectionally. 99.9% of all robot systems I know are still unidirectional data flow systems. That doesn't work. That's the single most inhibitor for progress of cognitive technologies in robot systems. Cognition is not something you put in a pipeline. It is something that is a network, has a network effect. It integrates all different things at the same time. With this approach, it has limits. Currently, with the constraint optimization problem, with that formulation, the system will not be able to explain its context. That's not there. There's another research paradigm, hypothesis there, the composition pattern, that I will talk about later, that we try to tackle that problem also. Another intermezzo, perception and control. What I've drawn here is a conceptual Bayesian network with 5 layers that, to my experience, is sufficiently concrete to explain the whole thing of perception and control to students, also to industrialists, and it's still simple enough to discuss. So I have 4 levels here. The lowest level, sensors and actuators, that's where the engineering system, the information flow is really grounded to the physical world. At the top, you have the mission, like assemble this piece of furniture. The mission is influencing all the tasks, taking screws, putting them in holes, taking the screwdriver, and so on. And between the tasks and the sensor and the actuators, you have these 2 difficult levels where 99% of the robotics research is focusing on. From the sensors, we try to extract features, sensor features, and then we try to associate these sensor features to object properties. So most of robotics is focused in these 2 middle layers, both for the perception and for the control. It's amazing how many times the same wheel has been reinvented in that layer. I'm long enough in the field to now witness my 4th wave of reinvention of letting robots open a door. That's the 4th wave of complete reinvention. in the sense that none of the current PhD students that are opening a door has any idea about how it was done 10 years ago, 20 years ago, and 30 years ago. That's a pity, but I understand that. That's because there are way too many papers published about these things. Another very important thing, all arrows here are bidirectional. It's the Bayesian network graphical notation that I use here. It suggests unidirectional information flow, but no, it's really bidirectional. Extremely important, bidirectionality again. If you put then some more terminology on top of that figure, I think we are completely ready to standardize all this terminology. It's out there for 30 years already. One of the important things to let the research be used in applications is that finally we, as a community, and that's a broad community, standardize our terminology. I've seen the same concept coming back in so many different terms. That's really, we should stop that. That's a responsibility of our community. And there's nothing that is missing. It's just a matter of doing it. This is the composition pattern. I'm not going to go into details, but the important things here is notice there is some hierarchy there. So the most important thing are these rectangles within rectangles. This hierarchy is not a traditional hierarchy of object-oriented design, of traditional robot architectures. It's not information hiding. The hierarchy here is embedding in knowledge contexts. That means the outermost rectangle that represents for me the place where you have to explicitly say in a formal way what context knowledge you're applying there. What are all the assumptions you make that closes the world for everything that is inside? And that idea, of course, repeats iteratively, recursively when you're going down. You see two similar rectangles on the top left and top right. For me, that's the smallest architectural primitive to work with. Compare that with building ROS nodes together. That's a completely different approach. I'm not going to go into detail, but that's a constructive approach to help build robot control architectures and at the same time give an explicit place to formally represented knowledge, and hence the simplest version of cognition. So the context or locality extremely important. ROS, so most of the software frameworks we are using in robotics, is completely the opposite. So one-line statement, ROS is the worst thing that could happen to the robotics community. I know that the public perception is completely different, but I'm willing to motivate that statement. Good. Going back to the MAR, to the public-private partnership, projects there have to define which step changes they are going to tackle. What step changes is a project going to solve? Here I've tried to make roughly 5 step changes in that particular order, from simple to more complex, that we can tackle and that we should tackle, I think. Again, it's a hypothesis I'm very happy to discuss about you. The ordering there is, it's not a coincidence, the same ordering that I had before in the different knowledge domains. Platform, task, object, environment, and the skill to glue everything together. The only difference between these orders is the context. How broad, how big is the closed world that you put around the robot software? And that is nicely extended step by step with these different step changes. So that's one possible way to define how to bring in cognition in robot systems. It's up to your community to take some of these things and try to put them into the road mapping exercise for the PPP projects, because PPP projects will only be funded if there is some reflection of the project ideas in the roadmap. Good. The first step, number 1 there, that's extremely simple to do. We just have to formalize this piece of knowledge that's out there for 50 years already. We all know that a robot system, or system of systems, consists of kinematic chains with kinematic joints, mechanical joints, actuators, transmissions, power converters. It's there for 50 years. Still, not one single standard about this. There's nothing there. Every lab encodes these things poorly over and over again in code that is not compatible with other code. That's a major problem of the robotics domain. A major problem. There's nothing stopping us from really standardizing these things and standardize them as an ontology, not just as a file format, but as a real ontology. There's nothing stopping us from doing that. So, with this I reach my conclusions. I really believe cognitive robot systems are a lot closer than we think. They're just waiting to be used in an industrial context. We're just doing the wrong things to make it happen. So as a community, roughly speaking, we should take the example of natural language, linguistics, things like WordNet, which have been developed as a community and become de facto standard that consolidate knowledge about natural language in a formal way. And we should extend it and make a skill net out of that. That means we have to extend the natural language with connections to how engineering systems can realize the actions that we express with these sentences. And that we can, how we can perceive these things, how we can make a sensory motor control. So the goal for me there would be to act as humans expect the machines to act. There's no reason to try to let them be human. That's a very interesting research domain, but I think it's a lot closer to industrial practice if you just try to act as humans expect. The hypothesis that I still have to make that transition to skillnet, or whatever it is going to be called, possible, is standardization. Look at successful domains. Speech, to a large extent, has been successful with the problems that we've seen before, but as a community thing, because there's a lot of standardization there. Consolidation. Only big industry can do standardization. The problem is in robotics there is no big industry, so there is no standardization. Probably Google is going to come out in 2 years with Android for robotics and they're going to impose a de facto standard on us. Whether we will like it or not, I don't know. But I see the danger there that they're going to own all robot platforms as they own most of the smartphone platforms now. Most of us here are academic. Well, we should try to change the system. Our system really does not work. We are stimulated to fragment, to find the smallest piece of difference between what we do and what other people do. We are not stimulated to consolidate. That's a problem. We should all together try to change the system. With this system, we are not going to achieve something. Another important message, from pipelines to networks. Pipelines do not work. You have to integrate all the things. And integration is putting a knowledge context around all the activities within that scope. And the last one, scale. Every PhD student, for me, should think at least in a systems of systems context. Most PhD students are just trying to get 5% better score at a certain benchmark. I'm a little bit exaggerating, but not too much. But you should think big. You can always then reduce your research to something that is graspable by one person, but you should have a very high scale ambition and context of thinking. Most of our researchers have a very, very, very narrow scale of thinking, and that's the wrong way. Again, the hypothesis there is, if we don't do it, industry will do it one way or another, and industry is going to be Google. I don't know of any other robotics industry that has these visions, that has the people on board in doing it. So we've been seeing a lot of technology that was created and grown and matured in Europe, move over the Atlantic, and people are going to make money out of it. Robotics is going to be the next money loser for Europe if we do not change it ourselves. Okay, from a technical point of view, bidirectionality. Bidirectionality, bidirectionality. I say it 3 times because everything I see in PhD thesis is pipelines, pipelines, pipelines. That's the most important technical aspect here. Okay, I'll conclude my presentation here.